Hello everyone, my name is Maurice Wilson, and for the summer I've been working with Jason Eastman on obtaining high-precision photometry of transiting exoplanets, in particular with the Minerva Observatory. The Minerva Observatory is a 4-telescope array with the mission of finding, confirming, and characterizing Earth-like exoplanets. Each telescope has a diameter of 0.7 meters, and what's unique about this observatory is that with it we can obtain a Doppler shift precision of 0.8 meters per second or less, as well as a photometric precision of less than 1 millimagnitude. And so with both of these goals being achieved, we gather high precision measurements which would allow us to precisely find those physical properties of those exoplanets. So this process of finding these physical properties precisely starts off with spectroscopy. And because we want to achieve that Doppler shift precision, we use bright stars. So this movie is simply showing that the wobble of the star, which is seen in the Doppler shift measurements, is due to the gravitational pull of that exoplanet revolving around it. So if we were to take spectra of this system, we would find a number that equals the mass of the planet times the sign of its inclination. And the inclination is simply put is the angle that describes the planet's the orbit of the planet's orientation with respect to the observer's line of sight. So if we know the inclination, we can solve for the mass of the planet. The problem here is that spectroscopy alone does not give us this inclination. That's where photometry comes in. So this movie is simply showing what a transit is and below how the light curve changes over time. So a transit is when a planet crosses the face of the star and the light curve dips and the light from the star decreases. So if the planet is transiting, photometry will allow us to get that inclination, and this is why. This movie is simply showing the relationship between your light curve and the inclination. So at different angles of inclination, you get a different looking light curve. So with this photometric data, we can find out what the inclination is and thus solve for the mass of the planet. Now with photometry, we can also figure out the radius of the planet. So my work begins with aperture photometry. So in order to create that nice looking light curve at the end of the day, I need to first figure out the flux of the star. And in order to do that, I need to get rid of what's known as the sky background. So here, I've just encircled the star. It's in the green region. And within the green region, you have the flux of the star as well as the sky background. Now, within this yellow annulus here, I can figure out what the sky background is. So my code can simply, you give me the coordinates, I find the centroid of the star, and then the script figures out the sky background and then subtracts that from the inner region, which leaves me with only this flux of the star. So because bright stars were used for the spectroscopy, I need to follow up and observe those exact same bright stars for the photometry. Here is a bright star that actually does have a transiting exoplanet around it. Now, if I wanted to analyze this star, I would run into two major problems. So, for one, in order to create that light curve, I also need to conduct relative photometry. And relative photometry requires the use of comparison stars. Now, comparison stars are similar in brightness and color to my primary target of interest. The problem here is where are other stars that are similar in brightness to this one? In this field of view, there are none. So how would I conduct that relative photometry? Secondly, a problem that's pretty evident is that in the process of creating this pretty image, the bright star has saturated the CCD. And when this saturation occurs, the data I've gathered on this bright star is no longer trustworthy. I can't truly figure out what astrophysics occurred here and what's going on. So these are two major problems that are very common for bright star photometry. So how do I tackle these? Well, you know a guy named Dr. John Johnson, and you can figure out anything. So he's standing next to one of the Minerva telescopes, and he's going to help me illustrate the concept of what relative photometry is. So let's imagine that Dr. John Johnson, being as enthusiastic as he is, monitors all 4 Minerva telescopes simultaneously. And despite the daylight and the clouds, he manages to get these nice images. And the concept here is that with one Minerva telescope, he can observe the primary target And with the other 3 Minerva telescopes, he can look at different patches of the sky to find those satisfactory comparison stars. So that's how it works. Rather than dealing with only one field of view, hoping that another bright star is within it, we have the power of Minerva to observe other patches of the sky and conduct relative photometry. Now, the actual analysis of relative photometry goes like this. Telescope 1 has observed WASP 52. And within this light curve, there's a lot of flux variation. We need to figure out where in this light curve is the exoplanet actually transiting? What is due to that? What is the other variation due to? What's going on here? In order to figure that out, we need the comparison stars. Now, the comparison stars are not variable in any way. So if you do see flux variation, it must be due to the atmospheric effects, because Minerva is a ground-based telescope and we have to deal with these kind of things. So what I do here is take the average of these 3 light curves and then divide that average under the primary target's flux, and you end up with a nice light curve like this one. And here, I've gotten rid of all the variation due to atmospheric effects, and now I truly see the astrophysical information I was looking for. And now we see, okay, the exoplanet did transit, that's why there's a dip in the light curve, and after the transit, the star remains constant. Good. Now this plot is simply a more aesthetic plot of the same data. But I want to show this because a model was fitted to this light curve. And that's what we do. Once we find a satisfactory model to fit to our light curve, then we can figure out precisely what the radius and mass of the exoplanet is. So the precision comes from the defocusing technique. And that this image is simply showing how a star can look at different focuses you use. And this is just an illustration of what a CCD is, and it has its pixels, and electrons are inside of each pixel. Now, thanks to previous speaker Anna Cologne, you all are experts at what a CCD is and how it works, so I don't need to explain that. But I will emphasize that a pixel has a maximum limit as to how many electrons it can contain. And so once it reaches that limit, saturation occurs, which is what we saw in the other image. Now, how do we stop this from happening? I'm dealing with bright stars. How do we stop this? That's where the defocusing technique comes in. And if you can imagine this star on, let's say, 2 of these pixels, all those photons being concentrated on 2 of these pixels, within a matter of seconds, certainly one of those pixels will saturate. By defocusing your star and dispersing the photons across more pixels, you have more pixels sharing that load of photons. Therefore, it's less likely that saturation would occur, and therefore, I get to increase the exposure time of observing these bright stars. And with such an increase in exposure time, and I'm talking about from 2 seconds to even 2 minutes of increase. With such an exposure time increase, that will lead to significantly reducing the flat fielding errors in our observations, and that is where the precision comes from. So, with the Minerva telescopes, using the defocusing technique, the stellar system 16 Cygni was observed. It has 2 stars here, and both of these are light curves for both of the stars. And in the process, 2.7 millimagnitude precision was achieved. That's pretty good considering how bright these stars are. Now, in the y-axis is relative magnitude, and the x-axis is time. So keep in mind, no transit occurred during this period of time, so it makes sense that it's pretty constant. But what I want you to take from this plot is simply that the precision was 2.7 millimagnitude, but this same data set proves that less than 1 millimagnitude precision was achieved here. And this is why. So in the y-axis is root mean square, and the x-axis is time scale. So what you need to take from this is simply that if you bend the data points in your light curve in such a way, then you will be able to see that you have achieved that less than 1 millimagnitude precision. So we start off with that 2.7 millimagnitude precision. Root mean square is 2.7 millimagnitude, and depending on how you bend it, you'll eventually reach less than 1 millimagnitude around the 3-minute time scale. Now, by time scale, I mean you're bending the light curve in such a way that, okay, 3 minutes of time equals 1 data point. And so after this bending, you have a new light curve, and with that light curve, this same data set has achieved less than 1 millimagnitude. So, in summary, I've helped create this photometry pipeline, thanks to Anna Cologne as well. And with my part of the software, you can get, before the observation even begins, you can give me a primary target, or you can give my script a list of primary targets, and it will give you 3 or however many comparison stars you want based on criteria such as brightness, color, and proximity to the primary target. Now, for after the observation, you can give my script your as many fits files as you want, and it will conduct relative and aperture photometry, even if the stars are defocused, and then spit out a light curve for you. So that's the software that I've helped create this summer, and Anna Cologne was, as you heard, focused on the data reduction side of things. And this is very important because with Minerva being a relatively new observatory, this software has features specialized for Minerva as well. Before the observation, if my script can give you those comparison stars as well as spit out a observation target file. And this target file can be read by the Minerva computers, which control the Minerva telescopes without the need for any human to touch a button. So, unfortunately, the Minerva telescopes are shut down currently due to monsoon season in Arizona. So, in order to create these scripts and this software, I've been practicing on other data from stars that I myself have not observed. However, I do have my list of targets that I will be able to observe in September, so I'm very much looking forward to that, and I'm looking forward to giving you all an update on what photometric precision I've achieved with my stars, and of course, furthermore, what physical properties I've found with the planets of interest. So, I'll be happy to give you that update later, but stay tuned, and you'll probably even see me at the AAS giving a poster on this. So thank you for listening.
Questions for Maurice? Rowan?
Very elegant presentation.
Oh, why, thank you.
I have a question, however.
Yes.
You have somewhere a list of stars and their positions and magnitudes programmed into your selection criteria.
No. So if you use this software, you can say WASP52. And my script will use Sinbad criteria. So it's similar to Sinbad. It's actually a package from Sinbad that's within Python. And so I'm basically taking the internet out of the equation. So you give me WASP52, my script will get, and you tell me how many comparison stars you want to find, my script will give you 3 or however many comparison stars. So no, there isn't a specified list. I'm using the database of Sinbad to find these comparison stars based on coordinates, brightness, and color.
So you decided on three comparison stars. How sensitive are your answers to 3 versus 4 versus 5 versus 6?
By sensitivity, exactly.
How the averages come out. In other words, you're trying to take into account that the bright star
Yes.
has backgrounds.
I see.
Trying to take out those backgrounds. The backgrounds differ for several reasons.
Mm-hmm.
Not only is the atmosphere different in different parts of the sky, somewhat, but also the distances will be different.
I understand your question now. So yes, different telescopes, you have to account for different things. And even with the comparison stars, I do try to find, it's based on proximity as well. So although we are looking at a different patch of the sky, we want to still look at a very close patch of the sky. So the air mass, for one, is going to be not so different. But secondly, to be as precise as possible and accurate, that's something we actually need to test. That's why I have yet to combine both ideas, defocusing as well as the multi-telescope capabilities of Minerva. So in September, I will be able to give you an update on exactly how we have been able to do that. But since Minerva is a relatively new observatory, we have yet to test that out, how well the data reduction part of the pipeline can handle those differences and things like that. So
it's also being rained on right now. So
yeah.
no problem.
Yeah.
Maria?
Yeah, I was wondering whether, do you have to tell your pipeline whether the image is in focus or not, or can you really just put in any image and it figures it out?
I've made the software very user friendly. So the one thing you will have to do as the user is decide what full width half maximum for the star, the aperture photometry. You decide how the aperture photometry is conducted. So if the star is 3 pixels in length, all you need to do is input 3 pixels, and then my software will do the aperture photometry. So I let the user decide what is the full width half maximum. Then for every single image, it can follow that same aperture photometry.
But having heard that question, I think one thing we can probably do is go into the FITS header where the focus value is recorded.
Oh, yes, because there's a correlation.
Calibrate based on the focus point, and then maybe it would be automated.
Yep, that is something that my advisor definitely said. That's something we're working towards doing. And once I combine both aspects and have a really nice data set, I'll be able to optimize that code to make it even more user-friendly. So, yeah.
One last question here.
So the defocusing technique and as well as this time averaging that you talked about.
The binning, yes.
How much does it depend upon atmospheric fluctuations? And that will again depend upon how far away your comparison stars are, right?
Yes, that's certainly something we have to test out. Yes, experimentally, basically, because we haven't used both. We have not observed. We haven't used both techniques yet. The multi-telescope aspect while using the defocusing technique. So, to be frank, we do have to test that out and figure out how much variation is significant to account for. So.
Yeah, so one of the things will be scintillation noise, and that scintillation noise will get averaged down the longer you can expose, which is yet another motivation for using defocused images, is it allows us to expose long enough to get scintillation beaten down as far as possible. But like Maurice said, we have to test it. All right, well, let's thank Maurice.